An infinite sequence is a sequence with infinitely many terms. We've talked about finding sums of finite sequences for arithmetic and geometric sequences. We've talked about finding the nth term in an arithmetic or geometric sequence. We're going to talk about infinite sequences and finding something called a limit. So if you consider the infinite sequence, 1, 1/2, 1/3, 1/4, 1/5, ... whose nth term, which I don't know why that says a sub 1, because it should say a sub n, is 1 over n. That means the next term would be 1 over 6, the next term is 1 over 7, 1 over 8, and so on. As the sequence goes on, what values do the terms appear to approach? So if we look at this in terms of decimals, it's a little bit easier to recognize. So you have 1, 1/2 is 0.5, 1/3 is approximately 0.33, 1/4 is 0.25, 1/5 is 0.20. Well, what's happening to those decimals? They're getting smaller. And how small are they going to get? Well, if you think about a term somewhere down the road, like 1 over 100, you're going to get 0.01. Or 1 over 1,000 is going to be 0.001. Well, I've already gone up to 1 over 1,000. The numbers keep getting smaller and smaller, and when numbers are getting smaller and smaller, we say that they approach 0. We've actually done this before, but we didn't call it a limit. We called it a horizontal asymptote. So a reminder, we talked about problems when we reviewed rational expressions like 2x plus 1 over 3x minus 4. And we found vertical and horizontal asymptotes. A vertical asymptote was a value of x that made the denominator equal to 0. And in this particular equation, if x is 4/3, then the denominator is 0, and you can't have 0 in the denominator of a fraction. So on a graph, at 4/3, there would be this dashed line that the graph doesn't cross or touch. But we also talked about horizontal asymptotes. And the way that we found horizontal asymptotes was we had a definition, which is reviewed here in these notes. If the greatest exponent of x in the numerator and denominator is the same, then the horizontal asymptote was the ratio of the coefficients in front of those terms. But if I change this slightly and make this 2x plus 1 over 3x squared minus 4, now the larger exponent of x is in the denominator, in which case the horizontal asymptote was y equals 0. In other words, it approaches the x-axis and it doesn't cross it. But if I change this again and I made the bigger exponent of x in the numerator, we said that there was no horizontal asymptote, or we wrote DNE for does not exist. Well, now instead of calling it a horizontal asymptote, we're going to call it a limit. Anytime we want to find the limit as n goes to infinity, in other words, as n gets bigger and bigger and bigger, of an expression like 1 over n, or 1 over n to the r power, if the denominator of a fraction keeps getting bigger and bigger and bigger, the fraction as a whole gets smaller and smaller and smaller, as we showed in this introductory example. So we say that the limit approaches 0, which is the same as the horizontal asymptote, and that's what we discovered here in this 1, 1/2, 1/3, 1/4, 1/5, ... One way to find a limit is to substitute large values in for n. So in example 1a, it says estimate the limit of 1/2, 7/9, 17 over 28, ... And then the rational expression at the end is the definition for finding each consecutive fraction. So when n is like when n is 1, so for first term, you get 1/2. And when n is 2, you get 7/9. And when n is 3, you get 17/28. So in order to determine what's happening, let's try plugging in a big number for n, like 100, or 1,000, or 10,000. I like to pick multiples of 10. So if I pick n is 100, and I plug it in and I evaluate that expression, I get approximately 0.02. If I plug in n is 1,000, I get approximately 0.002. So I bet if I put in 10,000, I probably get 0.0002. But you can tell as I put in larger and larger numbers for n, the output got smaller and smaller, which means that it's approaching 0. So we say the limit as n approaches infinity, that's how this is pronounced, of 2n squared minus 1 over n cubed plus 1 is 0. How about if I look at b? 1/3, 1/9, 1 over 27, dot, 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 1 over 3 to the n. 1 over 3 to the n is the definition, because when n is 1, you get 1/3. When n is 2, you get 1 over 3 squared, which is 9. When n is 3, you get 1 over 3 cubed, which is 27. So the next term would be 1 over 81. And the next one, I think, is 1 over 243. So what happens as you make the denominator bigger? So if I plug in n is 100, like I did in the previous problem, my output is 1.94 times 10 to the negative 48th power. Remember, if you do this in your calculator, you get an e. It says 1.94 e negative 48. That's the calculator's representation for scientific notation. Well, what is this? That means move the decimal 48 spaces to the left. That's an awfully small number. So it must be approaching 0. So the limit as n approaches infinity of 1 over 3 to the n is going to be 0. I'm going to show you these theorems for limits. However, they come back into play later in the semester or in a calculus course. You'll learn about limits. There are these properties of limits that say that if you have the limit of a sum of two expressions, you can separate it and find the limit of each expression and then add them together. A limit of a difference, you can find the limit of each expression and then subtract those answers. A limit of a product, you can find the limit of each expression and then multiply those answers. The limit of a quotient, you can find the limit of the numerator, limit of the denominator, and then divide them as long as the limit of the denominator is not 0. And the limit of a constant is just that constant. Remember, a constant is something that doesn't have a variable, so there would be nothing to plug in for. So the rules for finding the limit as x approaches infinity are the exact same rules I gave you when we did this for horizontal asymptotes. If the largest exponents of x, or n, or whatever variable, are the same in the numerator and denominator, then the limit of the ratio is the ratio of the coefficients of the terms containing the largest exponents. If the largest exponent is in the numerator, then there's no limit. If the largest exponent is in the denominator, then the limit is 0. So let's look at problem 2 and find the limit of each. I'm going to show you two ways of doing this. Here's the way I like to do it. So in part A, I want you to notice that the biggest exponent of n is in the numerator. There's no limit. I'm going to go down the column here. In C, the bigger exponent of n is in the numerator. There's no limit. In E, the biggest exponent of n in the numerator and denominator is the same. So the limit is the ratio of the coefficients, which is 3. In G, the bigger exponent of n is in the denominator, so it's 0. In B, the biggest exponent of n is the same. So the answer is the ratio of the coefficients. I'm going to skip D for a minute. Go to F. Be careful, because sometimes we don't put them in order. the bigger exponent of n is in the numerator. All right, let's talk about d and h for a second, because d and h have something a little bit different. They have that negative 1 to the nth power. So I'm going to use those properties of limits, and I'm going to separate these into two expressions, because we had a property of limits that said I can take the limit of this and the limit of this and then multiply them together. So the limit of the second fraction is going to be 1/5. But let's talk about the limit of negative 1 to the nth power. So what happens is I put in bigger and bigger numbers for n. So negative 1 to the first power is negative 1, but negative 1 to the second power is positive 1. Negative 1 to the third power is going to be negative 1, but negative 1 to the fourth power is 1. Well, what's happening? When the power is odd, the output is a negative. But when the power is even, the output is a positive. So if I try to find negative 1 to the 100th power, it's going to be 1. But negative 1 to the 101st power is going to be negative 1. Well, what's it approaching? It's not. It just keeps fluctuating between 1 and negative 1. Well, if it's not getting smaller and smaller, then how do I find its limit? You don't. Because of that negative 1 to the first, or negative 1 to the nth power, the limit is going to fluctuate. And if one of the limits does not exist, but the other one does, we're going to say does not exist times a number does not exist. Okay, I'm going to erase this because I'm going to go back and I'm going to show you the other way of doing this. This is the way that you're going to learn it in calculus. We're going to go back to those introductory fractions we had. The limit of 1 over n, I don't remember what it was. The limit as n approaches infinity of 1 over n we said was 0. And the limit as n approaches infinity of 1 over n to the r power is 0. So anytime what you're changing, the variable, is in the denominator of a fraction, the limit's going to approach 0 because you're making the denominator of the fraction bigger, so the fraction as a whole becomes smaller. So the other way of doing this is to divide everything by the biggest power of n. Well, in this one, the biggest power is n squared. So 3n squared over n squared is 3. 6 over n squared is 6 over n squared. And n over n squared is 1 over n. By the definitions we gave you at the very beginning, this goes to 0, and this goes to 0. Uh-oh, I have a 0 in the denominator. Can't have a 0 in the denominator. That's why it does not exist. In B, the biggest exponent is n squared. So if I divide everything by n squared, I get n squared over n squared, which is 1. 3n over n squared is 3 over n. And then 4 over n squared. And then in the denominator, n squared over n squared is 1 minus 1 over n squared. All of these go to 0. And I'm left with 1 over 1, which is 1. In C, the biggest exponent is n squared. So if I divide the numerator and denominator by n squared, I get 4 over 3 over n. This goes to 0. So you have 4 over 0, which does not exist. Doesn't really work so well for D and E. D and E, we talked about how if you have negative 1 to the nth power, it does not exist because it's just going to keep alternating between 1 and negative 1, so it's not actually approaching anything. E, the biggest exponent of n, is n to the first. So if you divide everything by n, you get 3 plus 6 over n. And then in the denominator, you get 1. Well, this goes to 0, and you're left with 3 over 1, which is 3. In F, the biggest exponent is n to the fourth. So you get 1 over n cubed minus 3 plus 4 over n to the fourth. That's in the numerator. And the denominator, you get 1 over n squared minus 1 over n to the fourth. Well, if these all go to 0, you're going to have a 0 in the denominator, which you can't have so it does not exist. And g, the biggest exponent of n, is n to the 7th, so you're going to get 4 over n to the 5th in the numerator and 3 in the denominator. Well, this goes to 0, and 0 divided by 3 is 0. If the common ratio of a geometric series is less than 1, the absolute value of it, then you can find the sum of an infinite geometric series. The only sum of an infinite series you can find is if the sum is geometric. If it's arithmetic, you cannot find its sum, because arithmetic sequences either get bigger forever or smaller forever. They don't approach a number. So we're going to use this formula, s is equal to a sub 1 over 1 minus r, to find the sum of an infinite geometric series. How do you know it's an infinite geometric series? Well, first of all, figure out if it's infinite. I know if it's infinite. It's got the little dots at the end. That ellipses at the end means it goes on forever. Second, check if it's arithmetic or if it's geometric. How do you know if it's geometric? Well, if there's a common ratio. Remember, you find the common ratio by dividing the second term by the first term. And if I divide the second term by the first term, I'm going to get 2 over 5. Then I'm going to check that, and I'm going to do 9.6 divided by 24 and see if I also get 2/5, or 0.4 if you like that better, which you do. So it must be geometric. If it's geometric and r is less than 1, then I can find the sum by doing the first term divided by 1 minus the common ratio. If you do this in your calculator, please put a set of parentheses around the denominator, or you're not going to get the right answer. 60 divided by 1 minus 0.4 is going to be 100. Because the numbers are getting smaller, eventually the numbers become so small that they're negligible, which is why the sum ends up being 100. Let's do this again in B. First of all, is it infinite? Well, the ellipses, the 3 dots at the end, tell me it is. Is it geometric? Well, the common ratio would be the second term divided by the first term, which is negative 1/2 or 0.5. Is 25 divided by negative 50 also negative 0.5? Well, yes, it is. So the sum is going to be the first term divided by 1 minus the common ratio. Be careful, because you're subtracting a negative, which is going to turn it into a positive. So 100 divided by parentheses 1 minus negative 0.5 is going to be about 66.7 or 66.6 repeating. The last thing that we're going to talk about is how to write a repeating decimal as a fraction. Now, a repeating decimal really is the same as an infinite geometric series, and I'm going to show you how it works, and then I'm going to show you the cheap and easy way. So let's just start with part A. I'm going to do it down here so I have more space. The numbers that are to the left of the decimal, we're going to leave those alone. But we're going to add to that the fraction of what's on the right-hand side. So 0.981 is also known as 981 thousandths. Since it's repeating, that means that it's repeating the 981. So now if I put another 981 after that, how many more decimal places will I go? Well, I'll go 3 more after that. Look what I did. I started with the 1,000 and then I tacked on 3 more zeros. And then the next 981 after that will be the previous term plus another 3 zeros. Ignoring this for now, we'll tack it back on in a little bit. This is an infinite geometric series. So to find the common ratio, I'm going to do the second term. Let's see, what is that, 1,000,000? And I'm going to divide it by the first term. And just do it in your calculator. And you're going to find out the common ratio is 0.001, which is good because we want r to be less than 0 or less than 1. So now I'm going to find the sum by doing the first term divided by 1 minus the common ratio. Remember, I put that in parentheses. I'm going to put that in parentheses too. So 981 over 1,000 divided by 1 minus 0.001. Hit math, enter, and you're going to find out that it's 109 over 111. Add back that 12, and the calculator is going to tell you it's 1441 over 111. This is the fraction that results in the repeating decimal 12.981981981981981981 forever and ever. Now that we've done it that way, now I'm going to show you the cheap and easy way. Nice thing about the graphing calculator is since you know it's a repeating decimal, if you type in 12.981981, you put this in several times, maybe fill up the screen, then hit math, enter, it's going to pop up 1441 over 111. So if you look at B, 12.42 repeating, notice what's repeating, just the 2. So in your graphing calculator, if you put in 12.4 and then you just keep putting in a whole bunch of 2's, and then you hit math, enter, it's going to pop up with 559 over 45. And that is the fraction that will result in the repeating decimal 12.42 repeating. And that's section 12.3 on infinite sequences and series.